see you.
Sir, now?
Yeah, now it has come.
Yeah.
It has come.
It is scrolling, sir?
Yeah, it's yes. You're right.
Oh, okay, sir. Okay.
Dr. Prashant, you can tell me when we should start. We will start.
Okay, sir. I will tell. Yes.
Sir, we will begin the program by 5 o'clock.
Okay, fine.
Yes, sir.
Good afternoon, Murthy.
Good afternoon, Dr. Pradeep.
Okay, nice to meet you.
Thank you, same.
Okay, so everything going well?
Yeah, fine.
Okay.
So maybe we will meet somewhere in April. I hope so.
Okay, we can meet.
Yeah, it all depends on what's happening now,
Okay. The condition is very difficult.
Yes.
Presently, you are at Chennai, isn't it?
No, I'm in Mumbai.
Okay.
Yeah. I stay in Mumbai.
Okay.
Parthiban is in Coimbatore.
Okay.
Yeah. He's in Coimbatore. He is my colleague. Yeah. Parthiban, once again, can you show your screen, please?
Yes,
Yeah,
sir. Now it is
okay, fine. Thank you.
Visible.
Thank you.
So I think we can start at sharp
Yeah.
5
Fine.
o'clock.
Yeah. Dr. Prashant, yes? I think he is on mute. Dr. Prashant is on mute.
Yes, sir.
Okay.
We can. Within 1 minute, we can start. Okay, Ms. Achadi,
Yeah.
let us
Good
start.
evening, everyone. Respected Principal Dr. T. Pradeep, our IQAC Coordinator, Mr. Sandosh R., our esteemed resource persons, Mr. R. Krishnamurthy and Mr. A. Parthiban, colleagues and dear friends. We welcome you to Energy and Environment, the 4-day national webinar series organized by the Department of Physics, Srinarayana College, Punalur. Let's begin the program with a prayer song. For this, I invite our final year degree student, Ms. Madhuri B. Over to you, Madhuri.
കൈവിടാതിഞ്ഞങ്ങളെ നാവികൻ നീ ഭവാബ്ദിക്കവരാവിവൻ തോണി നിൻപദം ഒന്നൊന്നായി എണ്ണി തൊട്ടെണ്ണും പൊരുളൊടുങ്ങിയാൽ നിന്നിടും ദ്രക്കുപോലുള്ളം നിന്നിൽ ആസ്പന്ദമാകണം അന്നവസ്ത്രാദി മുട്ടാതെ തന്നുരക്ഷിച്ചു ഞങ്ങളെ ധന്യരാക്കുന്ന നീയൊന്നു തന്നെ ഞങ്ങൾക്കു തമ്പുരാൻ ദൈവമേ കാത്തുകൊള്ളുക കൈവിടാതിങ്ങളെ നാവികൻ നീ ഭവാബ്ദിക്കവരാവിവൻ തോണി നിൻപദം.
Thank you, Madhuri. Srinarayana College, Punalur, named after the saint, poet, and philosopher Srinarayana Guru, is a center for higher education in the eastern side of Kollam district in Kerala. The Department of Physics has been one of the prominent departments in the college from its inception in 1965. The department began to offer undergraduate program in 1984 and has emerged into a postgraduate department in 2013. The webinar series entitled Energy and Environment will be focusing on different types of renewable energy such as wind energy, solar energy, and hydroelectric power. Eminent people with practical knowledge in the subject will be delivering these lectures. Now, I invite Dr. Prashant S., HOD, Department of Physics, to deliver the welcome address and to introduce the speakers. Over to you, Prashant, sir.
Thank you. Good evening, everyone. Respected Principal Dr. T. Pradeep, our distinguished resource persons, Mr. R. Krishnamurthy and Mr. A. Parthiban, organizing committee members of the program, colleagues, participants from other colleges, and dear students. Today, we are gathered here for inaugural talk in practical aspects of wind energy conversion, organized by Department of Physics, Srinarayana College, Punalur, in connection with National Webinar Series, Energy and Environment, mainly focusing renewable energy. Renewable energy is catching big attention today in India because of the difficulties behind the petroleum-based energy resources. Very recently, Petroleum Ministry also advised to replace LPG to electric cooking ranges. In this situation, pollution-free renewable energy resources like wind energy and solar energy emerge with the add-on advantages of low maintenance cost. Today, we have two eminent personalities in the field of wind energy with vast professional experience. In this warm occasion, I am very happy to welcome you all to the program. At the outset, I would like to welcome our Honorable Principal, Dr. T. Pradeep, without whose support, this webinar wouldn't have been possible. I welcome you, sir. Next, I welcome our resource persons, Mr. R. Krishnamurthy and Mr. A. Parthiban. I am very grateful to both humble personalities to spend their precious time to present in this webinar to share their valuable real-time experience to the participants. Both are from Continuum Green Energy is an independent power producer having operating plants in Tamil Nadu, Gujarat, Madhya Pradesh, and Maharashtra. Besides this, one of small hydroelectric projects with 10 megawatt is also being operated in Kulu district, Himachal Pradesh. Mr. R. Krishnamurthy, third child of late Ramachandran and Anandavalli, he is one of the alumni of SN College, Punalur, completed his PDC in 1976 and BTech Power Engineering from NIT Surathkal. Then he joined several well-known companies all over India in power sector. He is now settled in Mumbai and working as an electrical engineer in Continuum Green Energy. Moreover, Mr. Krishnamurthy is kind-hearted to our students. I am very proud to announce he is the sponsor of Ramachandran Memorial Merit Cum Means Scholarship in memory of his father, Ramachandran, from the academic year 2020 to 2021 onwards. I am happy to welcome you, sir.
Thank you.
Mr. A. Parthiban, a mechanical engineer by education, completed ME in thermal engineering from Annamalai University. He has over 18 years of experience in wind and solar project execution. Has extensive experience in project management and is resourceful at strategizing techniques for maximum utilization of manpower and machinery. He has installed more than 750 megawatts in Tamil Nadu and Maharashtra. I am happy to welcome you, sir.
Yes, sir. Thank you.
Now I welcome all organizing members of this webinar series. Last but not the least, I happily welcome faculty and students from various colleges who have joined us for this webinar. I welcome you all and wish you enjoying the program. Thank you.
Thank you, Shah. On principal, Dr. Over to you.
Thank you, Ashwati. I'm very happy that we have with us Krishnamurthy, an alumni of our college. And above all, he's an eminent personality in the field of energy. And he has worked with more than 5 or 6 companies during his lifespan. So he has got a lot of working knowledge in the area of energy. Okay, I'm very happy that Department of Physics is very honored, very much honored with the participation of a business group or a company that is having actual play in the region of power generation. So it will actually enlighten the students because they will get a very good exposure on what is going to happen in their future. So all of us know that it is not possible to progress without energy. Energy is very much important in development of a country, and renewable energy plays a very important role in that area. Without using renewable energy, we cannot progress. As all of you know that our petroleum resources are going to expire by 10 or 15 years. So we have to switch entirely to the wind energy, solar energy, hydro energy, etc. Okay, the team is a very well-known team we have with us. So they will lead us in the discussion of renewable energy and how it can be tapped and how we can, or they can also attract our students to the area of wind energy and other non-conventional energy area. So once again, I appreciate the efforts taken by Murthy in organizing this program. As our HOD pointed out, Prashant pointed out, we are very, very grateful to him for initiating a scholarship in our college. It is about to be fulfilled within 2-3 weeks. We'll be able to hand over the scholarship. And I think he will also visit our institution during this time. I welcome him. And I also welcome Parthiban for participating in this program and sharing his valuable experience.
Yes.
So I think it is even though this is a small seminar, small webinar, will have actually very good effect on the students. Okay, I'm not going to elaborate much on the aspects of energy. So we have with us the experts. Let us hear them. Okay, thank you.
Thank you, sir. Now it's time to begin the main aspect of today's webinar, the talk on the practical aspects of wind energy conservation, which will be jointly made by our resource persons, Mr. R. Krishnamurthy and Mr. A. Parthiban. I invite the resource persons to deliver their presentation. Over to you, sir.
Thank you, friends. And I think my colleague Parthiban will be presenting this slides. And of course, and as and when he wants me to join, I will be definitely joining. So Parthiban, over to you, please.
Yes, sir. Good evening to everyone. Yeah, welcome to today's webinar on wind energy conservation.
Please switch on your video. You're not able to. Yeah, that's it.
Yeah, we are viewing, sir.
Yeah, it's okay.
Yeah, first let us start with the different types of energy sources available in the earth. As of now, as Pradeep sir, Prashant sir, everybody has told, there are two types of energy sources in our globe. One is the renewable energy and another one is the non-renewable energy. Renewable energy, solar, wind, hydro, tidal, these are all the things will come under renewable energy. And non-renewable energies are coal, nuclear, thermal, petrol, diesel, everything. Each energy sources will have their own advantages and disadvantages. In olden days, that non-renewable energy sources like coal, nuclear, and diesel, petrol, everything has been used. It will be depleting at some point of time. As well said, it is around the next 10 to 15 years. all these non-renewable energy sources may be depleted. So as of now, this is the time to switch over from non-renewable energy to the renewable energy sources like wind and solar. So most probably in India now around 37 gigawatt of solar and wind energy is in line, and around 25 gigawatts of hydro is in pipeline. Everything is in operation. So what is the main disadvantages in non-renewable energy? Is the major thing. One is pollution, and regarding this nuclear, we cannot handle the final waste product of the output of the nuclear energy. And apart from this renewable energy, we have some little bit disadvantages. Now the technologies are improving, because in solar and wind energy, we cannot have a 24/7 continuous energy throughout the year, 365 days. For example, solar will have a output from morning around 7 o'clock to evening 6 o'clock only, and wind will have a seasonal variation. It is from in India average, if you see from April to October, there will be a high wind season. After that, there will be a less wind. So there is a small disadvantages in the renewable energy sources. So for that, now we are most R&Ds are doing on the battery storage, like hydrogen and other things and all now coming up. So now let us see what is wind. Wind is also one form of solar energy, which is caused due to uneven heating of the atmosphere due to sun. Because this Earth's surface is not a plain area, it has some water bodies, land surface, hilly terrain, and greener areas. And another one is the rotation of Earth. Due to these three phenomena, wind is forming. Everybody knows that Earth is surrounded by the atmosphere, which is filled with air. Air is nothing but it is a mixture of gas, solid, and liquid particles. Once the sun heats up the atmosphere in the top portion, it heats the atmosphere and the earth unevenly, because that water bodies will have some heating ratio, and land portion will have a different heating ratio. So due to this, there will be the pressure creation between land surface and water surface. So this difference in pressure creates the air to move from one place to another place, that is from sea area to land area. So that the movement of air is known wind. It is a general phenomena from high pressure that it goes to the low pressure. So that's why these seasonal variations are there all around the globe. Now we will go ahead with the wind turbine. What is wind turbine? Because in olden days, these wind turbines has been used for water harvesting and grains harnessing in around 1880s. After that, 1950s afterwards, this wind turbine has been used to produce the electric energy. In wind, that kinetic energy, because wind is in a form of kinetic energy. That kinetic energy is converted into mechanical energy by a rotor shaft, that is converted to electrical energy through generator. That is called a wind turbine. Wind turbine is nothing but a machine which converts kinetic energy to a final form of electrical energy. And most probably wind turbine will have three major components. One is foundation and tower, second one is nacelle, and third one is a rotor. Nacelle is like a heart of the body, heart of the wind turbine. It consists of all these gearbox, generators, and transformer, control panel, fluid couplings. Everything will consist in the nacelle only. And as of now, we have told in early stages, wind turbines is the capacity of 25 kilowatt, 50 kilowatt in 1950s and all. So once the revolution has started in the wind energy, in 1980s, it has come up to 500 kilowatt and 800,000 kilowatt and all. So after the 2000, that megawatt series has been started. That is 2 megawatt series, 3 megawatt. And as of now, as on today's latest news, it is up to 15 megawatt WTG has the capacity. Now they are developing a 15 megawatt wind turbine. That is the latest news in the globe. it is up to 15 megawatt. It has been developed. We have various turbines, 8 megawatt, 10 megawatt, and everything in the commercial operation. Now let us see the working principle of a wind turbine. I think everybody is seeing that wind turbine illustration. Yeah.
Yes, sir. Yes, sir.
Yeah. This is a simple wind turbine illustration. That is the tower portion, and that main thing is the nozzle, which is coupled with the rotor. Once the wind blows across the blade, there is the air difference between the front side and back side of the blade. So due to that rotor starts spinning. That is the initial action happened in the wind turbine. What is that? Once the air is across the blade, there will be a difference in pressure between the front side of the blade and back side. That creates lift and drag. So that's why this lift and drag will spin. It will start to spin the rotor. Once the rotor starts rotating, this low speed shaft is connected with the rotor, and it is coupled with the gearbox, which converts the higher speed to the generator, and the generator will produce the electricity. This is a simple form which will create the electricity. Just I will have that video. How does a wind turbine work? Sir, I think we are viewing the video, sir.
Yeah, please go ahead.
You've probably seen a wind farm, but do you know how wind force is converted into electrical energy? We are going to show you how a wind turbine works. Each wind turbine has a wind vane at the top that indicates the wind direction. This allows the turbine to rotate on the tower and face the wind. The blades also rotate on their axis for maximum resistance. Wind force, that is, the kinetic energy contained in moving air currents, spins the blades. These are designed to fully capture its energy. They can be as long as 60 meters each, but are made of very light and resistant materials for ease of movement. This is why they can produce energy even with very light winds, starting from about 11 kilometers per hour. With very strong winds, above 90 kilometers per hour, the blades are placed in the feathered position and the turbine stops spinning for safety reasons. The blades are attached to the wind turbine through the hub, which is coupled to the low-speed shaft. The low-speed shaft is given this name because it spins at the same speed of the blades, between 7 and 12 revolutions per minute. To produce electricity, it is necessary to increase the turning speed of the low-speed shaft. That is the mission of the gearbox, which raises the speed over 100 times and transfers it to the high-speed shaft. The high-speed shaft, that rotates at up to 1,500 revolutions per minute, is connected to a generator. The generator converts the kinetic energy into electricity, a source of energy that is easier to transport and use. The electricity produced in the generator is conducted through the interior of the tower to the base. There, a transformer raises the voltage for transport inside the wind farm. From each turbine, alternating current is sent to the substation through underground cables. Here, the voltage is increased again to feed it into the power grid and transport it to end consumers. This is how we use the wind to light cities, feed industries, schools, or hospitals, or operate our household appliances in a clean and sustainable way. Yeah. Murthy sir, you can add up some glimpses in this working principle, sir.
Yeah, just a minute. I just want to tell the people the transformer is shown below, and many a time the transformers are there for some machines are there in the nacelle. Some of them are there in the bottom of the tower. Some of them are external to the wind turbine itself. So that will come to that subsequent sites. Okay, thank you. Just we will go for the different types of wind turbines in the globe.
in different commercial markets. Okay. In yearly stage, we had a vertical axis. In the right side, there is a vertical axis turbine. In early 1950s and all, there is a vertical axis turbines only. It generates up to 100 kilowatt, 200 kilowatt, but it is less efficient. After that, what happens? It comes to the horizontal axis. Because based on the rotor axis, there are two types. One is vertical and the horizontal axis. And the horizontal axis, initial stage, there is a 2-blade turbines and 3-blade, multi-blade turbines and all in the market. But after that, 1980s, it is a more efficient. The 3-blade turbine is a more efficient and cost effective. So as of now, in all over the globe, there are 3-blade turbines. Horizontal axis is working in the market. These are the two types of turbines based on rotor axis. And another two types of turbines based on the rotor position, that is downwind, and one is the upwind turbine. In the upwind turbine, if you see in the right side photo, the wind will directly hit the rotor. It will face the first rotor will face it, and then the nozzle, it is on the upper side. So, but in the downwind side, it is opposite to that one. Once it crosses the nozzle, and it will opposite. It rotates in the anti-clockwise direction. So that's why it is a downwind rotor. But this downwind rotor is, as of now, it is not in market because due to this cost effective, and it is not that much efficient comparing to upwind rotor. So now all the turbines is in upwind rotor direction only, it will rotate. And third one, based on the locations, there are two types of turbines it has been installed. One is onshore and one is offshore. Up to 2000, everywhere it is in the onshore turbine only. In land area, in massive land area only, these turbines has been installed, and all is coupled with grid substation and this pooling substation concept and all. After 2000, it has came to the offshore. In seashore also, it has been started to install the wind turbines. This is due to mainly that capacity utilization factor. I will share the things in the next further slides on it. Because in the land area onshore turbine, we have a 6 to 9 months only peak generation. That is a wind season. Peak wind season will be around 6 to 9 months only. But in offshore turbine, if you see around 12 months throughout the year, we can have energy production. That is why now more researchers and things are going in an offshore turbine. One of the disadvantages in offshore turbine is capital cost is more comparing to onshore. Onshore turbine, if it is a 1 rupee, then offshore turbine will be 100 rupees. Like that, offshore turbine cost is more. So now the things are going on to have a cost-effective offshore turbines. So next we can have that wind farm. What is wind farm? We can say it is a group of wind turbines joined in a cooling substation, which is further connected to a grid substation. I will explain what are all these terminologies. Okay, wind turbine, you have seen each individual wind turbine, it will have a capacity of 2 megawatt, 3 megawatt, like that. So, for example, a 300 megawatt wind turbine of 3 megawatt means 100 WTGs. That is 100 WTGs has been installed in a particular area, which is connected via 33 kV line, that is HT line, because the power generated from the turbine needs to pulled up to the pooling substation. So for example, it is up to a 33 kV level. So 33 kV level has been stepped up to the 230 level at pooling substation, and from the pooling substation, the electricity has been transferred to the grid substation. From where the grid substation, the distribution network will start to our houses, to our factories, hospitals, everywhere. From the grid substation, the distribution will happen. So this is the form of wind turbine. And wind turbine, the wind farm consists of these access pathways to access the WTGs for operation and maintenance. And we have optical fiber cables, because all the wind turbine has been connected via optical fiber cable, that is OFC cable, to the SCADA system. For example, this 300 megawatt wind farm will have a central monitoring station at one place. From that place itself, we can monitor all these 100 turbines. We can switch off the turbine, we can switch on. Some operations can be done from here itself. some error attending, breakdowns can be attended from the CMS itself. So for that only this OFC cable has been used, because all this communication from the WTG to the central monitoring station has been taken through this OFC network only. Sir Murthy sir, you can WinForm, you can add up.
Yeah, it's okay. Go ahead with that.
Yes, yes sir. Okay. So this is one of the typical WinForm structure. You can have some wind turbines which is connected via grid network, and it is going to the pooling substation. From pooling substation to the grid substation. From there it goes to the distribution network. So now we can enter into the core subject, how the WinForm has been developed from the initial stage and how it go up to commissioning and operation and maintenance is happening in the WinForm developments. Practical things we can see of. So in mainly in the WinForm development, there are four main things are there. One is the micro-siting.
I think Parthiban, they got interchanged. I believe the slides. Just check it out, please. I think that something has happened in the slides. Maybe.
Yes, sir, this one.
Next slide, please. Next slide. Let me have a look at it. Okay, fine. Go ahead.
Okay, sir. Yeah. There are four main major activities in the development of the WinForm. Now, for the example, we are going with the onshore wind turbines. Okay. So one is the micro-siting and energy estimation. Second one is the detailed project report. Third one is the project execution. And fourth one is the commissioning and OMS part. These are the four main categories under the WinForm development. In micro-siting and energy estimation, we need to have a raw data for the wind resource assessment. Because without raw data, we cannot go ahead in the area. For example, I can say in India, Government of India has been installed a lot of MetMast. That MetMast is the instrument which will have the data for around 2 to 5 years. We need to have a raw data about the wind in that particular area, how much wind speed is there, annual wind speed is how much it is there, and wind pattern and wind shear ratios, temperature and air density. Everything has been collected in that MetMast only. In further, I will clear detail explain the things. Based on the raw data of the wind resource team, the developer will develop a turbine for that particular area, which type of turbine will be most effective, 2 megawatt or 3 megawatt, and tower height, how much tower height we can go ahead, and how much will be the rotor length, whether it may be of 50 meter or it may be of 60 meter. So based on this micro-siting and the raw data, wind raw data, that developers will design the WTG. After that, they will have an annual energy estimate. Because once you go for a commercial market, everything has been a financial thing. So developer need to say that, okay, my 2 megawatt turbine will have an annual energy estimate of this much, like that 60,000, 60 lakh units will be generated throughout the year. So like that, they will have an energy estimation. Mainly for energy estimation, we will have a power curve that will be in the detailed, we will have in further slides. Next one is the detailed project report. Detailed project report is nothing but like a budget and timeline. For having this 300 megawatt wind farm, what will be the budget and what will be the timeline? We need to complete this project within a 1 year. Like that, we have a detailed project report. Because based on the detailed project report only, the financial guys will work out on the equity and loans, because everything will be on the equity portion or in the loan type. Investment will be like that only. So based on the project report only, the further financial guys will take off the things. Next one is the project execution. Once everything has been completed, financial aspect, technical aspects, micro-siting, where the turbines will locate, for a 300 megawatt or the 100 WTGs, where will locate, which is the land parcel, everything has been done. It is all the theoretical workout, everything has been done. Apart from that, there is each state for India, each state will have a nodal agency for controlling these renewable energy sources. But I will go with the example of Tamil Nadu. Okay, in Tamil Nadu, there is an agency, NCS, Non-Conventional Energy Source Department, which will control all these renewable energy things. So So they will have some compliances, rules and regulations, criteria to develop a wind farm. So based on all these criteria, the company will have the rules, regulations and everything. They will got the approvals from the nodal agency. That is a state discom, like that there will be agencies. Once everything has been completed, paper approval works and technical financial aspects, everything has been completed, then real execution will start it on the ground level. For project execution, there are three departments will be there. One is a major power evacuation department, which will construct grid substation which will construct a pooling substation and 230 kV line and 33 kV HT line. EHV line and HT line will be constructed by a power evacuation team. Next one comes under as civil activities. Civil activities, the major portion is the foundation for the WTG. That is for the turbine. Main thing is the foundation, which will hold the tower and the whole part. The wind turbine will hold by the foundation only. And apart from that, access pathways, road, everything will be constructed by a civil department. Next one is the mechanical, which will take care of all these WTG materials and the erection, installation activities with the crane. And next one is the electrical department. Electrical department will do all this electrical works. USS yard, which will have this some transformers, meter, and this line portion. Everything will be taken care by electrical department. Once all the project activity is completed, we need to sell the power to somewhere. Then only we can generate the revenue. Okay. For that, in all over India, we had a 3 type of power purchase agreements we can go ahead. One is sell to board. That is, we can generate the power and we can sell the power to the state discom. For example, in Kerala, the KSEB is there, Kerala State Electricity Board. So in Palakkad, Attakati area, that there is a wind turbine that will generate the power and it will sell to the KSEB. So KSEB will pay to the customers. Further, KSEB will distribute the power to household, industries, and they will have the revenue. Second part is a captive energy. Captive energy, what means? You can have an industry. For example, you can have a tire factory at Palakkad. Then we can install a turbine and we can use the power for our industry itself. That is the second type. And third type, you can sell the power to the third party, other industries. You can generate the power by turbine and you can sell the power to all over India. Even from here, if you have a wind turbine in Gujarat, you can sell the power to Delhi. Delhi, some industries will be there. Even in Maharashtra, industries is there. So there are 3 types of power purchase agreement in India. These everything has been controlled and some agencies are there, like IEX, in Indian Electricity Exchange, things are there. So through that agencies also we can purchase the power. Next one is the final one is the commissioning and operation and maintenance. Once the WTG has been installed, we can have a commissioning portion. Commissioning portion is nothing but like a testing of all the equipments. All the components will be tested and it will be put in generation mode. Once the things has been in generation, this operation and maintenance will be in picture. This a whole wind farm will be handed over to the OMS team. So they will monitor and have that operation activities and maintenance activities. Wherever the breakdown happens, wherever the failure happens, they will do this maintenance and all. There will be a quarterly maintenance, half-yearly maintenance, and yearly maintenance schedules and all. So these things will be taken care by OMS team. All over the globe, if we had a 2 megawatt turbine with a capacity, with a height of 95 meter, that capacity utilization factor, that is how efficient the turbine will produce the power. It is around 25 to 32% of the efficient it will work. That is the capacity utilization factor of a particular wind farm.
Just a minute, I will explain this. I think people know about it. It is nothing but, supposing had this turbine would have been operating 24/7, 365 days, it will generate it as 100 units. But because of these wind patterns and so many other issues, like, there are grid issues, breakdown issues, etc., the energy generation will come down. That is what ultimately what exactly is being produced. When you look at the ratio, you will get the capacity utilization factor that is generally in the region of 25 to 32%. Thank you.
So we will go detailed with from the starting of how the wind farm is developing, that micrositing and energy estimation we will see. First department.
Parthipan, I just wanted to tell, because our students should be interested in this particular thing. And because Dr. Prashant was asking me specifically, so I just want to tell you, this is the most, I would say, crucial subject in a wind farm development. And this is where our students, area they can assess. Even if they are not engineers or something, they can be very useful in this, especially physics students can be, get associated this. And there are, courses, and I have given the websites, etc. You can go through. There are, online courses are there. You can get involved into that. Just look at this and be careful. And I would say give some attention to it. Thank you. Parthipan, please go ahead.
Yes, sir. Yes, sir. Once we plan to have a wind farm in particular area, for example, in Tamil Nadu, we had 3 zones. 3 zones is there. One is Coimbatore zone, second one is the Theni area, and third one is the Tirunelveli area, where the wind from Kerala, it passes through Palakkad Ghat, and another is the Sengotai Ghat. So like that, there is 3 areas in Tamil Nadu. So if we decided to have in the Coimbatore area, so at least we need to have a 2 to 5 years of data. How much years of data? Then it will be very accurate details we can have it. So minimum now the developers will have a minimum 2 to 5 years of the wind data. Based on the wind data only, all these wind farms has been designed. This is the basic criteria for the wind turbine, for planting the wind turbine. So based on this wind resource assessment only, we can define the wind turbine for that particular area. What is the physical condition, meteorology or geographical condition? Based on this, how it is a hilly terrain, or it is a plain area, or it may be of dense forest, like that, which is the suitable wind turbine. Because in market we had a lot of turbines. From, if you take from 1 megawatt, it goes up to, as of now, 8 to 10 megawatt turbines are there. So which turbine is very suitable for that particular area? And next, to define the layout of a wind farm, because as I said, in Tamil Nadu there is a rules and criteria for. I will explain some 2-3 criteria in this wind resource assessment. One turbine to another turbine, we need to have a certain area gap should be there, because that much, otherwise we cannot harness the maximum energy from the wind. So once the rotor diameter, for example, we had a V100 model. V100 is the rotor dia, 100 meter is the rotor dia. If you have a row wise against the wind direction, you need to have 5 times the diameter, that is 5D. 5 times the diameter, 500 meter from one turbine to another turbine in a row wise. At the same time, if you go on a column wise, it should have a 7 times. 7 into 100, 700 meters from one turbine to another turbine. Then only you can have a maximized wind output, the power output from the wind turbine. And another one criteria, if any damages or if any turbine has fall down, it should not touch any structure. It should not fall down on any manpower, man, material and these structures. So for that also, tower height plus half D plus 5 meter. Even if it fell down, it will not damage any structures. For that purpose, this type of criteria has been laid down. So based on the wind resource assessment, this layout also we can go ahead, and particularly to calculate the annual energy estimates and annual energy production, how much this wind farm will produce on annual basis. So for these 3 things, we need to have a wind resource assessment. So for example, I will show this one. So this is a met mast. It is like a steel structure in which sensors has been placed. So for example, 300 megawatt site, we need to install around 4 to 5 met mast with a 10 kilometer or 15 kilometer radius. We need to have a 4 to 5 met mast like that. So then only we can have a real data. Because in each area, if you have a 10 kilometer distance, that wind speed will vary, wind direction will vary, air density and roughness will vary from one particular area to another particular area. So for example, for 300 megawatt, we need to install around 4 to 5 met mast. Then we can study all the parameters, wind speed, how much per particular per minute, how the wind is, how the direction, how much speed it is there, and wind shear, wind turbulence, and density. Because the major factor plays in the power estimation. The power estimation is the air density. How much the air density will be there, and roughness of the area. Is there any turbulence is there or not? So all this 1 minute data has been recorded. So this is the metmast, which will have the sensor at different heights. For example, we need to install a 120 meter tower. Then metmast also we need to have a 120 meter. These sensors will be in a 120 meter, 110, 100 meter. There will be a 4 type of sensors. One is anemometer, and another one is the wind vane meter. Third one is the barometer and thermometer. So these 4 things. One is anemometer. Anemometer is used to have the wind speed, how much wind it is blowing in the particular area. And wind vane. Wind vane is the which direction the wind is blowing. For example, April to September there will be in one direction, and after that there will be a directional change. Only in peak wind season it will be near maximum in the single direction, even though that there is a small angle difference. But in after the peak, non-peak seasons, there will be different in each direction. The wind will blow in north or in east or in south. So for calculating the wind direction, the wind vane will be used. And this barometer and thermometer and all for air density and for temperature things, we can measure it. So this is one of the typical photo of this metmast. That wind vane and anemometer has been placed. This is the 120 meter tower. In the top of the 120 meter, we will place all these sensors. If you see, all these 4 sensors has been collected, the data has been collected in a data logger, which is kept downside of the wind metmast. There is a data logger. Each per minute data has been logged in the data logger. And after that, from the data logger, the data has been transferred to the central server. So from the central server itself, at any place in Bombay or in Gujarat or in Delhi, they can access the particular metmast and have the data. Per day data, they will take it and they will have a 2 to 5 years data. So they can have a detailed analysis. Okay, for this particular area, 2 megawatt will be suitable. Okay, we can go ahead with a 95 meter tower with a 100 meter rotor dia. Like that, based on the raw data, they will have an analysis and they will finalize the turbine. Based on the turbine design, they will estimate the power estimation. Sorry.
The website is given, so people can visit for further information. It's a very big subject, so I would suggest that students should take it in this particular area. Who are interested, they can go through, and all the details are available in that website.
Yeah, because you are all physics students, so this wind shear and wind turbulence, air density, pressure, and all your favorite subjects.
It's a good subject. It's worth pursuing.
Yes, sir. So government of India has been installed around, you can see around 300-400 masts all over the India it has started from the 1990s. So based on the wind pattern and average wind speed, all the India zone has been divided into 4 zones. That is high wind zone, medium, class 1, class 2, class 3, and class 4 zones. If the annual wind speed is from 8.5 to 10 meter, that is a class 1 zone. And the annual wind speed is 7.5 to 8.5, it is a class 2, that is a medium wind zone. And from 6 to 7.5 meter per second, it is a zone 3, class 3. And less than 6 meter, it is a very low wind zone. So as of now, if you see in all over India, this class 1 and class 2 sites, everything is completely filled, because this 37 gigawatt energy, wind energy, everything has been filled in this class 1 and class 2, class 3 also. Because after that, this class 3 has been further divided into A, B, C based on the average wind speed and this wind gust and all. So now all over India, that class 3 wind turbines is working on, class 3 B, C, it is going on.
And what happens is this, because the average wind speed is coming down, the rotor dia swept area is increasing. So that's how the developments are taking place. More energy is being captured.
Yes, sir.
Thank you.
Because in initial stage, if you see 1990s and 2000 and all, rotor dia is around 30 meter, 40 meter, 50 meter. Now the rotor dia has crossed 140 meter also. Because the blade length based on the swept area, power we can maximize the power output. So next one is the power curve. This is the major thing which will estimate the power of a wind turbine. Each wind turbine for 2 megawatt, each wind turbine have a typical power curve. This power curve is nothing but a graph that indicates the electrical output, that is the power output with respect to the different wind speeds. That is the power curve. Because, for example, you cannot have a continuous output, a continuous rated output for throughout the year or throughout the day. So based on the wind speed, power output will vary. In the power curve, there will be a three major portions. One is the cut-in speed, second is the rated speed, and third is the cut-out speed. What is cut-in speed? Because from 1 meter per second and all, that wind turbine will not work. Particular cut-in speed, we need it 3 meter, 4 meter like that. So that is called cut-in speed. Cut-in speed is the where the turbine will start generation of the power. Second one is the rated speed. Rated speed is the particular wind speed at which it will have a full capacity. For example, 2 megawatt. For a 2 megawatt means if it generates 2 megawatt at particular wind speed, 12 meter or 13 meter, that is the rated speed. Then third one is the cutout speed. Cutout speed is like it is for a safety purpose, because after 20 meter or 25 meter per second, there is a high wind during a monsoon season or any high pressure season. At that time, it crosses 25-30 meter. So at that time, there may be some damages to the blade, or the wind turbine can fall. So for that safety purpose, there is a cutout speed. So during the cutout speed, that wind turbine will stop production the energy. These are the three things we can have in the power curve: cut-in speed, rated speed, and cutout speed. So next one, mainly this power, how the power can be accessed, power can be calculated from the wind turbine. This power Pk is equal to rho AV cube by 2. This K and Cp is the theoretical constants, because that Cp is the maximum power coefficient. It is a theoretical value 0.25 to 0.45, and K is a constant 0.0013, which is used for the conversion of from kilowatt to horsepower. Mainly this rho AV is the major, that is the crucial things which is played in the power estimation of the windmill. Rho is the density, air density in that particular area, particular day, how much the air density is there. And A is the rotor swept area, how much length the rotor will be there. If you increase the rotor swept area, then power will also increase particularly. Then the wind speed, V is the wind speed. So this is the power curve in which we have mentioned this cut-in wind speed, rated wind speed, and cut-out wind speed. There are 4 regions. This is the region 1, in which the power output will be 0 only, because up to that that is up to the cut-in speed, the generation will not be there. It is in the, we can say it is a free trial motion. So from the cut-in speed, the turbine will start the generation. So from here, it will gradually increase. Once the wind speed is gradually increased, the power output will also increase. That is in the region 2. Region 3 is the rated cut-in speed, rated speed. At a particular wind speed, that capacity will attain the full power generation. 2 megawatt it will attain. So after that, how much it may be? For example, 12 meter per second, 2 megawatt will be rated capacity. From 12, even if it is 15 meter or 16 meter, that the turbine will produce only 2 megawatt only. That region 4 is the cutout wind speed, in which after the particular speed, wind speed 20-25 meter per second, that wind turbine will stop due to safety reasons. This is one of the typical power curve for 2 type of turbines. One is 600 kilowatt turbine, another one is a 2.1 megawatt, that is 2100 kilowatt turbine. For example, you can see here, there is a 2 type of power curve for same WTG. One is with a rotor dia S97 and another one is the rotor dia of S111. For power curve, for S97, the cut-in speed is 3.5. You can see here. I think it is visible.
Yeah, it's okay. You can make it little full scale if you want.
Yes, sir. Okay. And this is a PDF that's so we cannot go with.
Yeah.
So
Okay.
if, for example, this 2.1 S97, 3.5 meter per second, it will start power generation. So at 11 meter per second, it will reach at 2.1 megawatt. Up to 20 meter per second. Once the 20 meter per second wind speed reaches, the wind turbine will stop. But generally in this southern area of India, it will not go beyond 18 and all. 18, 20 tak jayenge, 20 tak it will go, but after 20 it will not go off. In some wind gust will be there for maybe some few minutes, 5 minutes like that. But maximum it will be less than 20 meter only, 20 meter per second only. This in southern area of part of India. For example, the same 2.1 turbine with a rotor dia of S111, the cut-in speed is 3 meter. So we can have a more output in S111. 111 type WTG, we can have a more output because at 3 meter per second itself, it will start generation. But this S97 will start in 3.5 only. And at the same time, that rated wind will be reached at 10 itself. This rated capacity 2.1 will reach. So this is one of the slides which will represent the tower height with capacity. If you see this parabolic circle, in olden days 225 kilowatt, 300 kilowatt, 500 kilowatt, 600 kilowatt turbines are there, which will have a tower height of 27 meter, 33, 40, 50 and all. After that is 1000 kilowatt, that is 1 megawatt series once come in picture, the tower height started 60, 70, 80. In nowadays, we had an average of 120 meter tower all over. It is installing all over in India is a 120 meter tower only because it will have a more efficient. It is a more efficient tower, and with the rotor dia of same 120, 140 like that, it is going on. For example, we are seeing that Statue of Liberty is a 305 meter and Eiffel Tower is a 1063 feet. Sorry, average onshore turbine as of now it is around 450 to 500 average tower of the height wind turbine now which is installing in the commercial market. Now apart from that, one of the tallest tower is the 574 feet. That is half of the Eiffel Tower we can have it. And another one example we have put in offshore turbine. Offshore turbine, the GE had a 13 megawatt turbine which will have a 248 meter tower height. It is in the around 5 to 10 kilometer around the seashore, which will have a 248 meter tower height with a 220 meter rotor dia. That means one rotor, that blade length is 107 meter. One blade length will be 107 meter. So this is one of the highest tower which is produced by GE. So now we can go ahead with the major components in the wind turbine. So now general things we have seen how the wind turbine works, principle, and how the wind farm can be set up. So based on this, so now we will see the major components and what are all the components in the nacelle and each and individual parts we can see as a picture also. We can have these slides. There are three major components in the wind turbine. One is nacelle, rotor, and tower. Rotor is a part which will combine the three blade with a hub. It is a simple one. Three blades will be coupled with a hub. It is called rotor. Next is the nacelle. Rotor is coupled with the nacelle, and nacelle will have a major components. All this gearbox, generator, transformer. As of now, in olden days, the transformer will be in the downside of the tower. Because it is outside the tower, there will be a separate yard will be there for a transformer and breaker, everything. But in new era, we had a transformer in the top of the nacelle itself. Nozzle is placed in around 300 feet height. In the same nozzle itself, transformer will be there.
Yeah,
And
that should be a
tower-
dry type. It's a dry type transformer. Okay.
Yeah, it is one of a dry type transformer which is kept in the top of the nozzle. And next one is the tower. Tower has a two types of tower are there. Globally, we are installing a lattice tower, and second one is like a tubular structure. Lattice tower, if you see that is mobile towers and all. Up to 60-80 meter tower height, these lattice towers has been used. Once the tower height is getting increased 100, 120, 140, then these tubular structures are being in the place. And there is a hybrid tower also. Both lattice and tubular structure has been placed, which is done by Suzlon. We'll have a two hybrid tower also. We will see in the further pictures also. And now we can go each one by one. So gearbox. First, nozzle we can have a we can go with a rotor. Rotor, we have a 3 blades, which is made up of a fiber. This less weight component will material is used for making a blade, which is around from 4 ton to 8 ton. Each blade will have around 8 tons, 8 metric tons. So this 3 blade is coupled in the hub. Hub is a steel portion which is coupled with the blade, which will have a pitch motor. There is a pitch mechanism in the rotor part, which have a pitch drive, pitch motor, which will rotate the blade individually from 0 degree to 90 degree. Because based on the wind speed, that blade can rotate. Blade can rotate self individually. Individual blades can be rotated. For that, only this pitch mechanism is used. Next one, the nozzle. This rotor has been coupled with the nozzle through low-speed shaft. Low-speed shaft has the same RPM, which is have a rotor. For a typical 1.5 megawatt turbine, rotor speed at a rated capacity is around 20. That same 20 RPM low-speed shaft also rotates. This low-speed shaft has been connected to the gearbox, which further speed up the things. Speed up the rotation through high-speed shaft to the generator. Because the gearbox will have a ratio of 1:110, 112 based on the capacity, minimum into 100, 1 into 100, there will be a gearbox ratio, 1:100. So the high-speed shaft that converts takes the energy from the gearbox, and it is coupled with the generator, which will further produce the electricity. It is like a same in our house. We are switching on the fan. Once we switch on the fan will rotate and air will flow to us. It is opposite. Once the wind is flowing, the turbine will rotate and the power will be generated. It is like we can see in bicycle olden days there will be a dynamo which will have a light in front of the bicycle. It is a small simple technology which will have a big components. Nozzle is like a nozzle. You will have all these components like what we have said, gearbox and everything. Next one is the tower. Tower we have told it is like a tubular structure is also there. A lattice tower is also there. In nowadays after 2010 we had a concrete towers also, which is cost effective comparing to your steel tower. Concrete towers is also there. But what is the disadvantages means we cannot have more height in the concrete towers. Around 100 meter or 120 meter tower, we can go with the concrete. Behind that, we need to use only tubular structures only. This we will further with examples of pictures. We can show this what are all the yaw motor, because everybody knows this wind will not blow in a single direction. All the 4 direction wind will have the flow. So based on the wind direction, the nozzle should rotate. For example, today the wind direction is from north. Tomorrow it goes to east. So that nozzle needs to yaw to the position to the east. For that mechanism, there is a yawing mechanism which will have a yaw drive, yaw motor. Because tubular structure, the tower is a permanent fixed structure. Above that, the nozzle has been placed. So the nozzle will rotate according to the wind direction. In which direction wind is blowing, So that blade and nozzle, it will total top section will be yawing will be done. And lot of sensors has been used: wind vane anemometer, and temperature sensors, vibration sensors. Lot of things has been utilized that I will go in the further slides also. And another one major thing is the control unit. There is a control unit in hub also, a small control unit, and another one in the nozzle also. And we had a main control panel at the bottom of the tower also. All these three control panels has been interconnected. All the data, whatever the sensor data or power data, whatever the data, everything has been integrated. And from the main controller, downside controller, that through OFC we have taken to the SCADA. From there only, all the instructions will be given. So I think you are seeing the one main picture of the nozzle. Everybody is viewing, sir, this generator. This is the nozzle, which will have the, you can see in the last portion of the nozzle, it is a transformer. After that, there is a generator. This is a generator. And after that, brake is there, this brake, mechanical brake, and yawing system is in the bottom of the nozzle, and gearbox and main bearings. This is the hub. And there is a separate hydraulic station, because we had a hydraulic brake system, gear oils, for all these things, hydraulic system with a particular pressure, specified pressure range, that oil should be flown. So for that, separate hydraulic stations is also there. And the pitch system, which will rotate the blade individually.
So usually Vestas, they give us the dry type transformer, which is located in the nozzle. Not everybody. Okay, like Suzlon, no, they don't give that. Inox, they don't give that transformer on the top nozzle. They're all on
downside.
Yeah.
So this is one of the blade structure. This is the blade which will be made up of fiber. This one will indicate the tip end. That is the tip end, which is a very lesser thickness. It is around even 20-30 mm thickness. It is up to the top, tip of the portion. And second, this one is the trailing edge. There are two edges. One is the trailing edge, and another one is the leading edge. Because this leading edge and trailing edge will rotate according to the wind speed. That is, I have told on a pitching. Each blade will pitch up to this, from a trailing edge to the leading edge. That is the reference point. And next one is the windward side and the leeward side. This 3 is the windward side, which will face the wind. This blade portion only face the wind, and the opposite side is the leeward side. So once the wind is blown in the windward side, that there is the pressure will be imbalance of pressure on the leeward side and the windward side. That will produce a lift and drag. That's why the blade is rotating. If you have this blade length, it is around 50 meter, 60 meter. Now around 75 meter blade and all, it is in the market, which will have around 8 metric ton to 12 metric ton. Each blade will have weighted for a 12 metric tons. And this is one of the Suzlon turbine. This is the blade. This is the blade section, which is coupled with a hub. Hub is a steel portion. This 3 blade has been coupled. This nose cone is for a safety purpose. And where the Suzlon is written, SU is that Suzlon, it is the nozzle portion, and down one is the tower. So now we will little bit go beyond that. Is all the pictures of individual components I am showing. In that much explanation will not be there, because all these are all the photographs of different parts, components inside the nozzle. Okay, so this is one of the nozzle mainframe. This is the skeleton of the mainframe, in which all this gearbox, generator, transformer, everything will be seated in the mainframe only. And second one is the nozzle cover. It is a fiber cover with a less weight, which will have a lifetime of around 20 to 25 years. And the next one is the rotor shaft. This rotor shaft is that coupled with the hub. That is coupled with the rotor. And this is the yawing mechanism and main bearing photos. Further, I will show that yaw drive and all. So this is the yaw drive. In each WTG, minimum 3 to 3, 4, 5, based on the capacity. Some WTG will have a 4 yaw motors. Some WTG will have a 5 yaw drive based on the weight of the nozzle, because it should, for example, the total tonnage of the tower section is around 150 to 200 metric ton, and nozzle as a massive component, around 60 metric ton to 80 metric ton is in the commercial market. And a hub will have a total three blade, and hub will have around 25 metric ton. So total around 80 to 100 metric tons need to rotate. For that purpose only this yaw drive is there, yaw drive and yaw rim, because this total nozzle is coupled on the base of the yaw drive. So this 100 metric ton will be rotated in all 360 degree based on the wind direction. This is a typical gearbox. It is like the same like we are in the two-wheeler, first gear, second gear. So the speed will increase from the low speed shaft to the high speed shaft. These are all some accessories: oil cooler and a lubrication system and filter motor, which is used for example, oil cooler. The gearbox there is a oil which should not go behind some temperature limit. So for maintaining the temperature limit, that oil cooler has been used. And these are all the hydraulic units and mechanical brakes. Because when we want to enter into the hub, we need to have a brake, because it should not start rotating. So to stop the rotation, and the manpower can work in the hub for maintenance activities or for attending the breakdown. So we had a brake system. This is a typical generator. This we can say heart of the wind turbine. This is the one which produces power. And another one thing, this main one thing, in everybody's mind there will be a doubt, because this rotor is rotating, nozzle is fixed. How the data has been transferred from hub to nozzle, and there is a pitch drive. For that, power needs to get into the hub through nozzle. So for that purpose only, we are using a slip ring inside the shaft. The slip ring, it is used to transfer the power and data from the nozzle to the hub. And these are all the control panels through which all this data has been integrated. And these are all the different types of sensor: vibration sensor, rotor speed sensor, incremental encoder is there, and north position sensor, yaw sensor, anemometer, wind vane, pressure sensor, hygrostat, and PTC, temperature, PT100 and all temperature sensors. Because this nozzle will have a different type of units, gearbox oil temperature it will monitor, and transformer temperature need to monitor. So all these have the sensors. These all sensors has been integrated in the control panel. This is the typical vibration sensors. Because if you add a much vibration, this vibration sensor will detect the vibration in X, Y, Z 3 direction itself. It can detect the vibrations. If it goes behind some vibration, it will give a signal to the control panel to stop the turbine. If there is a much turbulence in the wind, or any gust wind is there, so there the tower will vibrate. So if it goes behind the particular vibration, then it will instruct, it will give a signal to the turbine, the control panel, to switch off the turbine. And these are all different sensors: speed sensor, yaw sensors. Because once the nozzle is rotated for 360 degree, again it should re-rotate, because there is the cables, all the cables from the top of the nozzle, it comes to the down control panels. So cables should not twist. For that purpose, once the nozzle has been completed, it's 360 degree, it will re-rotate to the 0 degree. For that, north direction will have kept as a reference. For that only, the north position sensor has been used. And this is a typical wind vane for wind direction and wind speed for measuring, because based on the wind direction only, this total yawing will happen. For maintaining the temperature in the control panels and in nozzles and all, this hygrostat and thermostat is utilized. For example, if the temperature exceeds 35 degrees Celsius, this thermostat will give you indication to the cooling fans. It will start. The cooling fan will start. It will start blowing the air, so the temperature will fall. These are the temperature sensors. What is the temperature of the gearbox, main bearing, generator, and nozzle atmospheric temperature? Everything has been measured. This is a hub in which this 3 blade has been joined. It is a steel structure which will have each pitch system. 3 pitching system will be there for 3 blades. This is the pitch drive. Each blade will have an individual pitch drive. Based on the wind speed, the blade will rotate. These are the nose cones in front of the hub. It is for safety purpose. It has been designed. These are all the different control panels has been used in the wind turbine. Major thing, this tower will have a four components, 4 sections of tower will be there. As of now, 4 and 5 sections are also there. Each sections will have a different weighted average. For example, bottom section will have around 40 to 50 metric ton. Next section will be around 35 metric ton. Next is 30, 25. So overall, if you see, it will be tower section will be around 150 metric ton to 200 metric ton. As of now, it is available in the market. So this is one of the picture which represents the 3 different type of turbines for a same capacity. Turbine capacity is 2.1 megawatt, but with a different type of tower height and rotor diameter. If you see first one, which is have a 80-meter tower and will have a 88-meter rotor dia. This rotor dia is 88 meter. And second one, if you see, that is a 90-meter tower with a 97-meter rotor dia. If you compare with this 80-meter tower, it will have a 21.4% higher swept area and 12.5% higher hub height, and 25% more energy can be produced from 80-meter tower. If you see the third one, which is 90-meter tower with a triple one, that is 111-meter rotor dia, which will have a 46% more energy than this 80-meter tower. For example, if the 80-meter tower produces 100 kilowatt, the same 90-meter tower height with a triple one rotor dia will produce 146 kilowatt at the same wind speed. This is the one what we have told. This is a hybrid tower. If you see the bottom section, it is a lattice tower with a tubular structure. So this is only handled by Suzlon. Apart from that, other vendors will have only a tubular tower. This hybrid concept has been introduced by Suzlon. It is one of our Indian manufacturer. This is the specification, technical specification of this particular 2.1 megawatt with S97 and S111 rotor dia. This 2.1, this S97 model is particularly designed for a class 3A wind zone, which had a cut-in wind speed of 3.5 and 11 meter per second is the rated wind speed, and cutout is 20 meter per second. The same 2.1 with a triple on rotor dia, 3 meter per second itself, it will start producing energy. And it will achieve 2.1 at a 10 meter per second. This is the one of the main technical specification of the turbine. Murthy sir, Apart from that, we will go for the next installation part. You can add up.
Yeah,
some,
yeah, yeah. You can explain. You can explain. Please go ahead.
Yes, sir. Yeah.
Just you can just
As
run through.
of now, yes, sir. As of now, we have seen all the technical specifications, how the things has been designed, and how this micro-setting of energy estimation has been done. Now we will see some pictures of how it has been installed in the ground level. Once we decide, we go ahead with our 2 megawatt turbine. Per land, we need to purchase the land, and each WTG location, we need to have a soil test. Because we need to bore a 10-meter drill, and we will collect the soil samples and we will send to the laboratory to have a chemical properties of the soil and to have a safe bearing capacity. For example, modern windmills, we need to have a 20 metric ton per meter square safe bearing capacity. Then only we can install a tower. If it is less than 20 meter per per square meter, we need to go ahead for a re-engineering. So this is the first activity in the wind turbine installation. We need to check the soil properties. Once the soil properties has been checked and all the design foundation design parameters has been completed, we need to start excavation. For example, this what we have shown is a 2 megawatt turbine. It is a 20 meter dia and 2 meter depth. We need to excavate the ground for 20 meter dia with a 2 meter depth, and we need to have a sand bedding, because that will have a cushion impact of the total tonnage. Because if you see the total WTG, it will be around 250 to 300 metric ton, which will have that sand bedding. This is the first figure is the sand bedding, and after that we have a plain cement concrete, because there should not be any rust which will touch the soil, should not touch with the steel portions. There will be a center portion, there will be a pipes, PVC pipes, which will carry a cable, because this power cable will pass through this PVC pipes and it will take it out. And these are all the anchor cage which hold the total tower setup, and these are all the steel reinforcement. For example, 2 megawatt tower, we had a 35 metric ton steel you need to use for this foundation. Once the steel foundation has everything has been reinforced, we will start the foundation activities. So once the foundation activities is completed, we need to have a curing for 10 days. So once the foundation is completed, after 10 days, we will start installation activities with the tower. Before that, we need to dump all these WTG materials, tower, nacelle, rotor, hub, everything need to place nearby the foundation, and the crane should be marched. For example, this 2 megawatt tower, we need to use 600 metric ton crane to install total WTG. These 4 sections of tower section will be installed one by one. And finally, we will install the nacelle and blade. These are all the photos, how the crane is installing the nacelle and rotor. Once the installation activity of the turbine is completed, parallelly this 33 kV, that is a HT line network and yard or tariff meter, where the meter will be kept, because from there only the revenue point will start. So this 33 kV HT line and yard work parallelly it will start. So this is one of the final photograph of the completed yard, in which the transformer is in the downside. So this all the wind turbines has been connected through 33 kV network, and it is further connected to the pooling substation, in which all these 300 megawatt will be pooled in the pooling substation up to a 33 kV level. And from the pooling substation 33 kV level, it has been stepped up to 230 kV level, and further it is transmitted to grid substation through EHV lines. These EHV extra high voltage lines also constructed by developers, which will connect with the grid substation. From there, distribution network will start. So once the installation activity has been completed, we need to go ahead for a commissioning, because we need to put the turbine in the generation mode. So all the components have some pre-checks. Electrical checks will be there, then some visual checks will be there. So these are all the pre-commissioning activities. Once everything has been commissioned, pre-commissioned, then we need to have some approvals from particular nodal agencies. commissioning approvals, safety certificate, everything, all the approvals we got it. Then the particular day, commissioning day, the WTG will be put in generation mode. Once the WTG is in generation mode, then that particular wind farm will be handed over to the operation and maintenance team. This operation and maintenance team generally will have around 2 to 3 people for 20 to 30 turbines. If we had a 300 megawatt wind farm, around 20 people will be there. A day-night shift will be there, and they will attend all the breakdowns, failures, and there will be a preventive maintenance, scheduled maintenance, everything will be there. So these all things further throughout the life. For example, all the wind turbines has been life cycle of 20 years. For next further 20 years, this OMS team will take care of the wind farm. Yes, sir, Murthy sir.
Thank you, Parthiban. Thank you for the nice presentation. Yeah, yes, sir. I think if any specific anything is there, you can ask.
Yeah, we are eager to have any questions, queries from students, sir.
We would like to say that, we are given a general presentation, and I particularly stressed because we had a discussion with Dr. Prashant. He is saying how it will be useful. I wanted to say that this will be this wind energy conversion, where graduates or postgraduates from physics can look into it. One is wind resource assessment, and second is energy exchanges, power trading. There are the two areas where they can do, and of course, both of them are vast subjects. There are a lot of, things are involved in. And the rest is okay, executions, the selection of turbines and all those things. Of course, some technicalities are involved, so that is separate. But we can have both beginning and the end. In both the places, you will find as a graduate or postgraduate of in physics, you can definitely get take interest in that. You can get associated.
Yes, Parthiban sir, actually, here the wind turbine, about the wind turbine, the size of the wind turbine, just we assume, it's one leaf actually length up to 10 floor building, no?
Yes, sir. It is 50 meter to 60, 75 meter now blade is there, sir. Individual blade.
Yeah. Actually, the total height of the windmill is up to around 36 floor building, like a height, I think.
Yeah. It is now in India. It is 120 meter tower, and all 140 is also in India. 140 meter tower is the highest tower, sir. 140 meter tower height.
Yeah.
But if you look at from the ground to the tip, naturally you got to add that D/2 also you have to add. That will give you the total height of the turbine.
Yeah, that's why I am asking, because the students are looking from downwards. It looks like small, but the size of the windmill and the size of one leaf I saw, it's transporting from Thuthukudi to Tirunelveli. When I was traveling through, so I saw a large truck is transporting this one leaf even.
You see, there is a lift also inside. In olden days, there was not lift inside. Now there is a lift to go up, and in the nacelle itself is like a big house. You can say it's a big house. There are so many generators and all those things. Once you go inside, you will come to know that it's quite big. It looks apparently it looks so small.
Particularly nacelle, if you see, it is around like a 10 to 15 meter length and 8 meter width. It is like a big conference hall.
Yeah.
Hello, I'm asking a curiosity rising. So, what is the material that we are using for manufacturing this blade?
Sir, FRP, sir. FRP, fiber reinforced plastic.
Now I have seen some plants near Kerala, in Kerala.
Yes, sir.
Where wood has been used as a component of that
Yes, sir. In commercial market, it is FRP, sir. For domestic purpose, we are using wooden blades. Also, we are using in domestic purpose.
Okay.
In
Okay,
fact,
come on.
I have read yesterday's message that even Vestas has signed agreement with one of the companies in Europe where was started manufacturing wooden towers also.
Okay.
So even there are, changes keeps on changing. The point is economics. Basically it's all driven by necessity. So lots of changes are taking place. Material they keep innovating. It's not like a static. This technology is not static. It's continuously evolving.
Okay.
Yeah.
Thank you.
Actually, around the early times in Germany, they used the wooden windmill. This is
Yeah.
started
Yes,
from.
Yeah, with that wind turbine has been started from wooden only, sir. Because in the olden stages, it is used for water harvesting and this grains and all harnessing. They have used this wind turbine.
Parthiban, you can switch on your video, no?
Yeah.
Yeah.
Yes, sir. Any other questions? Anything else?
Yeah, Murthy sir, another question. What is the financial comparison with this wind energy and another petroleum-like products,
Yeah.
petroleum energy, thermal power stations?
You see, let me put it this way. Now, Parthiban was mentioning in the beginning, there are three types of power purchase agreement we can have. You see, like sale to board, which was subjected to feed-in tariff. Okay, it was actually feed-in tariff. It's called feed-in tariff. Nowadays, they are those competitive bids are come up. So we have 2 rupees 50 paisa, 60 paisa is what we are getting it. Okay, so it is going on, and thermal, of course, what happened? They are also producing, but the point is that we wanted to, the renewable energy is becoming cheaper because of competitive bidding. It so is being sold at that point of time, that point of Swan, and this thermal. When you look at the capital cost, something like the more or less per megawatt, it comes to around 6 crores. Am I right, Parthiban? Around 5.5 to 6 crores per megawatt.
Wind it will comes around 7, sir, 6 to 7.
6 to 7. That depends on this one, high end one. So it's around that. And because this is not a wind farm as such. Each wind turbine itself is you can call it as a machine. So you will find a 2 megawatt will cost you something like 11-12 crores. It will cost. Does it answer your question, Dr. Prashant? I think you're muted.
Yes, sir. Yes, understood. Actually, within what is the maintenance cost within 25 years around?
Yeah, Parthiban, you can answer that.
Annually, the 2 megawatt, for example, 2 megawatt turbine will cost around 15 to 20 lakhs because all the customers will have a comprehensive AMC with the developer itself, because this is a massive structure and all these cranes and all required. So it is around 15 lakhs to 20 lakhs versus 2 megawatt turbine. Per year it will increase 5%. We can increase up to the 10th year. Then there will be a small further increase to 7 to 8%. Base price is 15 lakhs.
We are talking on a wind farm level, okay, not a single turbine or something like that. We are talking on a large scale wind farms.
Yeah.
Okay, thank you.
Thank you, sir, for that illuminating section. Is there any more questions that need to be answered? Okay, looks like everyone has cleared their queries and doubts.
Yeah,
Now,
one of my requests to the Prashant sir, you can have a visit to our wind farm also.
Yeah, that's a fantastic. So when you don't have to know it, Dr. Prashant has got a number of Mr. Parthiban. You can directly dial him, and it is in Coimbatore only. Udmalpet is very near to Kerala. Absolutely not an issue. Please visit. You can also, incidentally, you can also see we have a co-located solar farm also, which is 55 megawatt. Okay, so we have a solar farm as well as we have a wind farm. You can just take as your students for a let us say education trip. Yeah, please do that.
Nowadays in the syllabus, there is a industrial visit is there, no?
Yeah,
Yeah, one day you can plan it.
Parthiban can be contacted. He is available there. You can coordinate with him. Right?
Yeah.
Thank you.
Yes.
Thank you. That will be nice.
Thank you.
Yeah.
I will be.
Okay. Thank you, sir. Now, the link to the feedback form is posted in the YouTube comment section as well as in the Google Meet chat box. I request the participants to kindly fill the form. Now, I invite our first year MSc student, Lakshmi Suresh, to deliver the vote of thanks. Over to you, Lakshmi.
Good evening, everyone. Respected Principal, Dr. T. Pradeep, distinguished resource persons, Mr. R. Krishnamurthy and Mr. A. Parthiban, teachers and dear friends. The task assigned to me is to deliver the vote of thanks. First of all, I would like to express my sincere gratitude to our principal, Dr. T. Pradeep, for the support and guidance he has given for this endeavor. Now, I extend my gratitude to our resource persons, Mr. R. Krishnamurthy and Mr. A. Parthiban, for the interesting and illuminating session on behalf of Department of Physics and the entire organizing team. I thank both of you for taking time off your busy schedules to be with us today. Next, I would like to express my gratitude to our IQAC coordinator, Mr. Santosh R, for his immense support and encouragement. Thank you, sir. Now, I convey my sincere thanks to Dr. Prashant S, HOD, Department of Physics, who is also the coordinator of this webinar, for your hard work and determination that made this webinar possible. Next, I extend my sincere gratitude to the faculty members in the Department of Physics, Dr. Radish R, Ms. Lakshmi R, Dr. Anuja J. Babu, Dr. Sandeep K. Nair, Dr. Kavita V.S., and Ms. Arya Lakshmi for their enthusiasm and support. Next, I thank Mr. Adul TB, Assistant Professor, Department of Mathematics, who made sure that this program would take place without any technical glitches. I would also like to thank Ms. Ashwati Anilkumar, Assistant Professor, Department of English, for the lively anchoring. Last but not the least, I extend my heartfelt gratitude to faculty members and students who have joined with us today for your valuable participation. Thank you all.
Thank you, Lakshmi. With a vote of thanks, we have reached the end of today's section. Once again, I thank each and every one of you for joining with us. And till the next section on the webinar series, this is Ashwati Anilkumar signing off. Thank you.
Thank you, Dr. Prashant, Dr. Pradeep. Thank you for giving me an opportunity to myself.
Okay, thank you very much.
Thank you, sir.
Welcome,
Thank you, sir.
Thank you.